cause of death for college students in America.
Really?
Second only to accidental death. Interesting.
Where does 18 to I'm recording? Yeah. All right, so we're gonna dive into some more equilibrium calculations today. And today we're going to get into the most difficult versions of these calculations that you'll do in this course in particular. And so we're expanding or focusing in on that mass action table. We've used it for stoichiometry. We used it for limiting reactants. And whenever we ran out of one of the reactants, that was the smallest value of X that we could have in the table. And so we would use that value of X for the whole table. We used it for kinetics. And we came up with X going from 0 up to a maximum amount, and over time, as that reaction would change over time, that was the kinetics piece. And now we're getting into equilibrium. And so we have this thing called the ICE table. Some schools call it the RICE table, which is reaction, initial, chemical, and equilibrium, or initial change and equilibrium. It's just the mass action table. The same thing we've been using all semester. And so here's a typical problem that we would have, which would be an equilibrium problem. So under certain conditions, the equilibrium constant Kc for the decomposition of phosphorus pentachloride, PCl5, into phosphorus trichloride and chlorine is 0.0211. Before we go any further in a problem like this, look at this number. What information do you have in that number? That's the equilibrium constant. So this is one of the things I want to train you to do, not just dive into the numbers and the calculation, but have a little stop sign there, and how you stop at a stop sign and you look, at all the different directions, you kind of get a lay of the land. Whenever you see an equilibrium constant, I want you to pause and think about what it's telling you. So it's 0.0211. So that tells you something about this reaction. Which is more abundant, reactants or products? Reactants are more abundant because it's less than 1. If it was 1, you'd have essentially equal reactants and equal products. If it was just A turns into B, you would have exactly equal A and B if it was an equilibrium constant of 1. Since this is less than 1, the equilibrium lies on the PCl5 side. You're going to have more PCl5 than you have PCl3 or chlorine because it's less than 1. Okay, so we've sort of stopped at that equilibrium constant. We kind of know, all right, whenever we do this problem, the equilibrium concentrations are going to favor PCl5. And so then what are the equilibrium concentrations of all three of these species if we started with PCl5 at a concentration of 1 molar? Okay. Now, a lot of times we think of, when we see molarity, we think of aqueous concentrations. And when we get to acid-base, they'll all be aqueous concentrations. It'll be some acid dissolved in water, etc. This is strange. This is a gas phase reaction. But you could still have 1 mole of gas in a liter container. And that's 1 mole per liter of solution. The container contains all of the species. And so you could still talk about molarity. So don't be bothered by that. It's just 1 mole per liter of solution. The reactants and the products are in the same container, so they're all in the same liter. And so we could deal with molarity even though everything's a gas. Okay, so there's nothing that ties molarity to, say, an aqueous concentration. Okay, so we have all of these gases up here, but we're talking about in terms of concentration. So we start with 1 mole of this PCl5. We have 0 PCl3 and 0 chlorine. And then we have the change row. So we find this double arrow here, and that's where these this table sort of divided in reactants and products. So these are products, and this is the single reactant. So that's where we get the minus X and plus X. So the reactant is going away, and we're producing products, and so those are growing. So that's where we have the plus X and so on. So then we get to the equilibrium row, and so we have this equilibrium concentration. 1 molar minus X, so this is going to be the equilibrium concentration of the PCl5. And then, anything added to 0 is going to be that thing. So we have plus X in terms of our products. And we can write this out in terms of an equilibrium constant expression, the equation that we did last time. So here's the equilibrium constant expression, and we just substitute in all the X pieces So we have two x's on top and then the 1 minus x on bottom. And so we end up with the equilibrium constant expression, which is an equation. Okay. We can simplify that, make it x squared on top. And we know from the problem that this is equal to 0.0211. So we have an equation now, one equation, one unknown. The only problem is it's not in an easily solvable form. And so we want to go ahead and multiply both sides by that 1 minus x. And then we want to get everything on one side to sort of set it up like a quadratic equation in standard form. So this is your goal. If you end up with a quadratic equation, is to get it into this standard form where you have ax squared plus bx plus c. It's plus c, but c happens to be negative, okay? So that's c is minus 0.0211. So you can kind of see where this is going. We have the quadratic equation in standard form, and we can go and find the quadratic formula. Is everybody cool with it so far? Yes. Yeah, so when we multiplied this piece over to the other side, so we ended up with this over here. So 1 minus x here. Yeah, and so that goes in there, and it also goes in here. So that's where it became the, and it's on the right side of the equal sign. So when we moved it over there, then the sign flipped. And so the minus 0.0211x became positive when we moved it to the other side of the equal sign. And then the positive 0.0211 became negative when we moved it over to the other side. So there's a couple of steps in going from this piece right here up to this right here, okay? Now that also brings up a point. If you're going through the notes and you see something that confuses you, certainly ask, but then later go through the video with pencil and paper and actually do the work yourself as if you're doing the problem. In fact, you might start with the problem, do it all by yourself, and then turn the video back on and follow the logic, okay, just to make sure you got it all. So then we have the quadratic formula here. So we put in the b and the 4 and the ac and 2a, etc., and we have the two solutions. Now, how do we keep track of our two solutions? Well, notice there's this plus minus here, and you can label your x's with plus minus. And so when you label the x plus, you're using the positive version of that plus minus. So you can say the positive or x plus root is putting all those numbers in there, you get 0.135. Okay. And then if you use the negative version of that, you can label that with x minus, and that's just indicating that's when you use the minus sign in that plus minus formula. And you get this root, negative 0.156. Now, both of those are solutions to this quadratic formula. And so this has always been something that bothered students in this course. You get two concentrations. Which one do you use? Okay. And so there's two answers. And so you have to think about which answer makes sense and which one doesn't. This top one is good because it produces positive concentrations. If we put it back into that ice table and look to see what happens at the equilibrium row, we're going to have positive concentrations. If we use this one, it produces nonsense. We put that into the table and it produces negative concentrations. And so we'll see that in the next page, but I want to make sure you have time to write down the details.
Is it possible to have both positives?
I've never seen it. They might be both positive here, but when you do the ice table calculations and put them in for X, it'll produce negative concentrations. Yeah, and one of them, there'll always be one that makes sense and one that doesn't. Yeah. Okay. I see y'all writing furiously. Well, we've got a little bit of time, so I'm going to let you wait. Any questions about the order of operations on this? what I do, because it's difficult to do this in one shot on a calculator, is I go ahead and like subtract. I calculate this piece and write that number down. Then I square that and take the difference, and then I go ahead and hit the square root. So I calculate this one, then this one, take the difference, take the square root, and then I subtract it or add it to this number. So I go ahead and write down these three intermediate results. And most importantly, getting to the square root, I write down that result. And so then I can take this number plus that number, and then this number minus that number, and I get my two roots, okay? And then divide by 2. So do it in pieces so that you don't make mistakes, okay? So let's look at the ramifications. Notice we're using the minus root when x is equal to negative 0.156. This is what the ice table looks like. See, I put that negative root here in for x in all these places. And so I have 0 minus 0.156. So it produces a negative concentration at equilibrium. And even more, or just as absurd, when I put it in here for x, I have 1 minus a negative x. And so this grew. So my PCl5, I started with 1 mole per liter, and now I have 1.56 moles per liter. And it came out of like an impossibility. These got negative. Well, where'd that come from? You know, if I've got nothing, I can't get anything else if I've got nothing. So it is absurd. It doesn't make sense to have equilibrium go backwards when it really should be going forwards. So that's a bogus root. And so here's the proper root. I put in that positive value, 0.135, here and here, and then subtract it there, and I end up with 0.865 is my equilibrium concentration of PCl5, and then 0.135 for the others. So that's very nice. And so we can check our work. So we've got our equilibrium rho, and we know the equilibrium constant value. So let's go ahead and check our work. Let's calculate the equilibrium constant. So here's our equilibrium constant expression. We put in the numbers from that equilibrium rho, and we get 0.0207. And that's great. That's close enough. It's not exact, but we have rounding, uncertainties and so on. So we got 0.0207. Hey, that's good enough for me. Yes?
So we're trying to go back to the number that we originally were given.
Yeah, so we're just checking our work. We did the table calculation, and we're putting those numbers in there. And what do you know, we're getting now the crazy thing is, if we were to take this number and square it, right, these two times each other and divide by that number, we would also get 0.0211, right? Because this is a root for that quadratic equation. So it is a valid mathematical answer, which would give 0.0211, but it's a nonsensical scientific answer. So this is the only thing that drives people crazy about the quadratic formulas. You get two roots, but one of those roots makes sense and the other one does not. Okay. So I guess this is an example of the most difficult type of problem that we have in terms of the ice tables. So let me just pause and make sure that everything's clear for you. Now, I don't really like using the quadratic equation. It's long and tedious. There's lots of rooms to make mistakes. And so I'm going to teach you a couple of tricks now that you can use to avoid it. And there's certain situations where this trick works well and other situations when it doesn't work so well. This is an example where it works moderately well, okay? And so let's look. So simplifying assumptions. Let's make some simplifying assumptions to avoid the quadratic equation. And if you notice in your notes, this title is a little different. I modified it like 5 minutes before class. So just make a note on this slide. This is a simplifying assumption, okay? What did we know from this equilibrium constant expression? I'm going to review that. What do we know from this since it's less than 1? The reactants are abundant. So what does that tell you about X? it's going to be smallish, right? It kind of depends upon the equilibrium constant. It's 0.02. That's not that small. It's 2 times 10 to the minus 1. But in some of these, like weak acids, it's be like 2 times 10 to the minus 5. It'd be 0.00002, which means X is really small. Okay, this one X is, it's 2%. X is going to be roughly, a few percent. It's not going to be a lot. Okay, so what does that mean we can assume? Look at that. Look at what I've just done in that equation. You see the assumption? I said 1 minus X is, let's just guess and say it's 1. Let's just say X is so small that I can't tell I subtracted it from 1. Right? You got $1 and I took away a penny. You pretty much have $1. Okay? You could probably get the convenience store person to go ahead and just take the 99 cents. They're like, yeah, close enough. Right? All right, so that's what we're talking about. This is a simplifying assumption. Let's see how good it is. Okay? So now we have a much simpler equation. We don't have to use the quadratic formula because we got rid of that X. We have X squared is equal to 1. It used to be 1 minus X times this, but now it's just 1 times this. Now we can just take the square root. So X is the square root of 1 times 0.0211, which is much, much easier. So X is 0.145. It used to be 0.135. The accurate calculation was 0.135. So we're off a little bit, but not much. Okay, do you see how this simplifies things? This is a simplifying assumption. And so let's see. Let me pause here. Just make sure that everything is clear to what we're doing with the simplifying assumption. Why can we assume X is small? Is much less than 1. It's mostly less than 1. It's smallish. If we had a equilibrium constant was something times 10 to the minus 3, 10 to the minus 4, 10 to the minus 5, this would be a rock solid assumption. 10 to the minus 2, you'll see. Let's look at the error. Okay. So we go ahead and put these in the ICE table. These are our equilibrium concentrations. 0 plus X is 0.145, 0.145. We assume that X was small here, so we have 1 here. Now that doesn't make scientific sense really, because where'd the 0.145 come from? Right? None of our reactant went away, and yet we have some product. Okay, but let's go ahead and check our error. So we calculated this with the quadratic formula or quadratic equation. And that's the more accurate one. So we'll call that our literature value, okay? And we'll take the difference and divide by the literature value times 100%. So our error is 7.4%. That's not bad, but it's not great, okay? It'd be nice if it was less than 5%, okay? And once again, it's as bad as it is because our equilibrium constant is 0.02. I mean, that's less than 1, but it's not a lot less than 1. When we get into acids and bases, these equilibrium constants are going to be times 10 to the minus 5, times 10 to the minus 7, times 10 to the minus 8, really, really less than 1. And so this rock solid assumption will be good. So 7.4% error in the PCl3 concentration and the Cl2 concentration. What's the percent error in the PCl5 concentration? Well, that would be 1 minus the 0.865, which we got from the quadratic equation, divided by the 0.865. So that's 16% error. So that's pretty big. It's 84% right. Right? The other is 93% right. Hey, that's not bad. Okay. We could make it better by going ahead and subtracting this X piece from the 1. So let's go ahead and do that. Let's make it a little better and go ahead and subtract that 0.145 from 1. And so we get 0.855. And so we assumed X was small. We calculated it. And then we put it back in as if it's not small. And that made our concentration better for the for the PCl5. So let's calculate our percent error on that one. So now our error, we're a bit low. We're at minus 1.2% error. So it came out as less than the quadratic equation value because these were higher than the quadratic equation value. So these were higher. The assumption produced a little bit more product than the actual result. But now that we've got incorrect products and incorrect reactants, we can calculate what our K is. This produces a K of 0.0246, which is higher than our actual K. And so that's going to be 17% error. So what we've done is we've pushed our error to the equilibrium constant, and we've gotten pretty accurate equilibrium concentrations. So this is a great assumption, a great tool that you can use. We'll do another one that goes the other way when K is greater than 1. Okay, so you can make these simplifying assumptions in both cases. If K is huge or if K is small, you can simplify things. Yeah.
If we use this way on the test, we have to prove the error.
No. In fact, I'm really just showing you the error calculations just to kind of train your mind into thinking about percent errors. Okay. You'll use those a fair bit in organic for like percent yield and things like that. But I just wanted to show you how good the assumption is. And it's decent. 16% error, 17% error is too high for me. I don't really like that. But I'm just showing you sort of an intermediate case when that assumption is okay, but not great. Okay. When we get to the acid-base reactions, these assumptions are going to be great. So let's look at one where the equilibrium constant is greater than 1. So here, this is a pretty hefty equilibrium constant, 776. So here's my double-headed arrow. That's where it divides the reactants and the products. These are all aqueous. So we're going to have, aqueous concentrations and molarity. So we have iodine, aqueous iodine reacting with the iodide ion, and we're getting the triiodide ion. We start with 1 molar concentrations of both of the reactants, 0 products, and then we're going to move in the forward direction with these minus X's and this plus X. So this is where sort of memorizing a procedure and not knowing the science will really destroy you. You think you're doing the problem right, but you got it all backwards because you're not thinking scientifically. You can't assume that X is small in this case. Why? Your equilibrium constant is huge, right? It's going to go to the products. And so you can't just say, oh, I'll just assume X is small. You can't do that in this case because the equilibrium constant being 776 tells you this reaction is going to go in the forward direction a long way in the forward direction. So X is going to be actually very close to 1. It's going to be almost all products when we're done and very little reactants because that ratio of products over reactants is 776. Okay. So I really don't want to do the quadratic equation though. And so can we figure out a way to get by that?
Maybe change maybe negative 1?
No, but you're thinking right. What can we do to X? We assumed it was 0 last time.
Assume infinity?
Infinity, so we can't get infinity out of it. What's the maximum it can be? 1. Okay, if we say X is 1, what have we done? We've pushed it all the way to the products. Is it going to stay there? No, but it's a good starting point. Okay, so what if we push this all the way to products and it wants to be a product? It's only going to come back a little bit. And so we could rewrite the X's coming in the reverse direction and X's would be small. Does everybody see the logic? When push it, if it says, I want to go all the way to products, you say, okay, go all the way to products. and now I'll calculate how much you come back. And you're only coming back a little bit. So this is kind of a strange way. It's not really strange. It's just a clever way. Should I pat myself on the back? You go all the way to products and come back a little bit. And so hang with me on this. Everybody, wake yourselves up. Okay. We have this. We could do the quadratic formula. So let me just show you how ugly that equation is. And that's no fun. Okay. This is just the equilibrium constant expression showing you the quadratic equation. And I realize it's not that hard. We could do it, okay? But, let's try to avoid it if we can. Okay, so look at this table. Look what I've done to the ice table. I've taken this, and now I've added 2 more rows. Yes? Oh, okay. I've added 2 more rows. And these 2 rows go all the way. And then we have a new initial setup. So what does go all the way mean? That means my x's are 1, so I'm subtracting all the way. So I'm going all the way to 0 for the iodine and all the way to 0 for the iodide. Okay, and that means I have 1 mole of triiodide ion. So that's my new initial setup. It's not at equilibrium because I have zeros there, and nature hates zeros. It's gonna give you something. Then when they say nature abhors a vacuum, right? It's like there's got to be some iodide and some iodine in this equilibrium. So now this is the thing that freaks people out. Look at my positive and negative signs. It's running backwards. What? Yeah, so here's my double-headed arrow, and these are reactants. And this is the product, okay? And I went all the way to the end, okay? I went down here, and I've pushed it too far. So now this is the reactant, and these are the products, okay? So this bottom piece is a new problem. It's a new ice table. It's just now I've gone stoichiometrically. I've coupled 2 problems. I've made a limiting reactant problem, and I ran it all the way to the end. And now I'm doing the ice table in reverse. And so what is going to be down here at equilibrium? It's going to be 1 minus x. 1 minus x. But I know that my equilibrium constant wants to stay on the product side. Or I should put over here. Stay on the product side. Okay? And so x is going to be small. It's not going to come back very far. And so then I'm going to have plus x, because 0 plus anything is going to be significant. Right? So even though x is really small, if I add that to 0, I can't assume that x is 0. It's anything plus 0 is going to be measurable, right? And so we have plus x's here, but this x is insignificant when compared to 1. It's going to be a really small number. And so we've avoided the quadratic formula by pushing it stoichiometrically all the way to products and then coming back just a little bit. This is a technique. I think there's one of these problems in the lab. Have y'all done equilibrium in the lab already?
Yeah, but not to this extent.
Okay, yeah, there's one in the lab that's much easier to do if you do it this way. And you can avoid the quadratic formula. You shove it all the way to products and come back a little bit, and you can do the problem in a real simple step. So here's our equilibrium constant expression. Okay. We still have this reaction written in the forward direction, so we're going to still keep K as the iodide, over the I2 and the I minus. Okay, so it's still written out like this. This is the I3 minus, and that's the I2 times the I minus. Okay, and we know that the top one we're assuming is 1. And then this is the x squared in the denominator. So we can rearrange this where x is 1 over 776. So you see x is going to be a small number, 0.0359. It's nice to know the quadratic formula. If you're doing this for your research, you would just go ahead and hammer your way through it. But a lot of times we're training you to do what we call back of the envelope calculations. We just want you to estimate things and be good at that. And so these simplifying assumptions allow you to get really close to the answer. And so let's check this out. What if I did the equilibrium, I mean, if I did the quadratic equation for this, I would get 0.0353, okay? And you guys can check that if you want on your own. And so the quadratic formula produces an x of 0.0353. My assumption gives me 0.0359. And so that is 0.8% error. So that's great. And that's because the equilibrium constant is so much greater than 1 that it only comes back a slight amount, and x is really small.
I guess the equation that is highlighted and it says ugly, how can we avoid? If you were to plug in the 0.0359 into that, you're saying that should give you back 776? I guess my question is, how do you check your answer? Is there another equation you can use, or do you have to use solely that one to check your answer?
No, we could plug it into, we could take 1 over this number squared. Like we could plug it back into this equation here and see if we got the 776. Okay. Yeah. Okay. And we would, yeah. So that's kind of strange. We've taken that ice table and added 2 more rows. But you see this piece right here this is like a stoichiometry calculation or limiting reactant. So we pushed it all the way by running out of our reactants. And that just happened that they matched, and so they both went to 0. But that may not be the case, right? You may have one go to 0 and the other still have some stuff there. And then you run it backwards. And then you would have a minus x on the product side and plus x is over here. And you might be able to assume that, like let's say we had 2 moles here. And so then this would be 1 molar here, and it would be plus x, so this would be 1 plus x. And so we would assume if x is small here, it's small there, and so this would roughly equal 1. And so we wouldn't even have an x squared. We'd have 1 over 1 times x and solve for x. And we would see, how much we have, so at equilibrium. So this just is a really good tool to be able to use this mass action table to push equilibrium forward or backwards. When you're doing a limiting reactant problem, you're pushing it all the way to products, but nature doesn't ever stay there. It's going to come back and achieve some equilibrium, and it'll be good. Okay. So we checked our work with the quadratic there, and we could also check it with the other thing. So that's all the equilibrium constant calculations for now, but I've got some extra stuff in here just to get us ready for the acid-base things. So these next few notes is sort of just an intro to acids and bases. It's not a lot of writing. There's a lot of text on there, but you don't have to write it all down. It's just vocabulary. And so let's just go ahead, in the time we have remaining, get you guys thinking about acids and bases, because we're going to apply equilibrium to acids and bases and get into pH and pOH and all of those kinds of things, since that's such a common part of our world. So we're going to identify acids and bases, and then this idea of a conjugate acid-base pair, and then we're going to write some equations for these ionization reactions. And then we'll talk about water, because water can act as an acid or a base. So let's dive in and see what an acid is. So this Bronsted and Lowry came up with a good definition of acid-base. And that is that a compound that donates a proton. So that sounds all very quantum mechanic-y, but if you're looking at, let's just say water, for example. If I take the hydrogen atom, then it's taking its electron with it. But if I just push the hydrogen over here with its plus charge, a positively charged hydrogen only has 1 electron, a positively charged hydrogen is just a proton. So that's what it's talking about. You're just taking this lone pairs and it's stealing the nucleus over here and leaving the negative electron on this one. And so this produces an H H3O plus molecule or ion and an OH minus. So a hydronium ion and a hydroxide ion. And so this is an acid-base reaction. The water here, this water is acting as an acid and donating a proton to this water. This water is accepting a proton, and so that makes it a base. If it was HCl, okay, HCl, it can donate that proton and make H3O plus and Cl minus. So the chlorine donated just the proton and kept the electron, and so it's negative, and you have the proton going on to water. And so this would be an acid-base compound or acid-base reaction. So anyway, when you're talking about proton donation, that's what we're talking about, acid-base reactions. It was really funny. My friend in graduate school would always come over to our house, and my wife's an accountant, and my friend's obviously a physical chemist. We were in graduate school together, and Phil started dating Nancy, and so I told Jennifer that Phil's going to bring Nancy over, and she was like, fantastic, someone to talk to, okay? And I didn't tell her that Nancy's in graduate school in physics, okay? And so we're all at the table talking about all kinds of physics and everything, and Jennifer's looking at me like, man, you're a jerk. We got into an argument over proton donation.
Oh, no.
And so she said, we were talking, and something, I don't know how the subject came up, but Nancy at the dinner table said, well, proton donation doesn't occur. Okay, and she's thinking like a physicist, right? And this is Gen Chem. This is like the basis of acid-base chemistry, and the room got silent. Phil and I are looking at each other like, oh my gosh, we can't believe she said that. And Jennifer's like, what just happened? Right? And we both jumped on Nancy like, how can you say that? Acid-base chemistry, protons are donated all the time and everything. So it was really funny. And so Jennifer, after they left, Jennifer says, what is Nancy majoring in? I said, oh yeah, she's majoring in physics. And Jennifer was like, Arr. So anyway, that's our Phil and Nancy story. Yeah, that's right. So yeah, I don't know what context that she was thinking where it doesn't occur, but in aqueous solution, proton donation happens all the time. In fact, you would be dead if it didn't, because the pH of your blood is buffered using proton donation. So acids, they can be both organic and inorganic. A lot of times they're cations that contain hydrogen or donatable protons, and anions that contain donatable protons. So like an example of an organic acid would be, and you can write these organic molecules in many different ways, like C2H4O2, and that's acetic acid. But that formula is useless because it has 4 hydrogens on there, but only one of them is donatable. So how would you know? And this is where we get into a little bit of organic chemistry in this course, okay? So let me write out the structure of acetic acid. It's this right here. And this little wedges and dashes, remember your Vesper shapes are supposed to indicate the proton coming or the hydrogen coming out of the board or going back into the board. Then we have a carboxylic acid here. So a carbon double bonded to one oxygen, single bonded to another oxygen, and that oxygen has a donatable proton on it. This is the acid group, and this is the acid proton. So notice how writing the molecular formula is not very useful. Writing the structure is not very convenient, okay? Because try typing that into a word processor, okay? So what do? There's a thing called a line structure formula. And so that's when we write out CH3COOH. You see, it can be written on one line, and it still tells you what's in the molecule. So this is the line structure formula for acetic acid. You have the CH3, which these are not acidic protons. They do not come off the molecule, okay? This one does. And so this one, you can add, let's say, add water to it. And this produces H3O plus CH3COO minus. And so you have the anion and the cation, right? So this is a line structure formula, very convenient for you to use. You know, this up here is just not very convenient. The acetate anion would be C2H3O2 minus. But again, why, you know, it's just not very helpful. But this line structure formula is very helpful. And you can even write it without the subscript if you're being lazy. CH3COOH. It's good to go ahead and write the COO just to kind of designate the difference between this O and that O. Okay? So that's a lot of times it's not CO2, it's just COO and a minus sign. But you'll see it sometimes CO2. But if you're really being proper, it's best to write COO so you know it's a carboxylic acid group. Okay, so these are different acids. And then bases, again, ionic compounds that contain hydroxide are just obviously bases like barium hydroxide, sodium hydroxide. But organic molecules like amines can be a base. So let's look at ammonia. So NH3, it has those lone pairs on top. We can add that to water. And one of these protons on water is attacked by those lone pairs. It's stolen off of water. And now we have this compound. That whole thing is charged positive. And a hydroxide. So here's an amine. So a nitrogen-containing compound that is hydrogens attached to it or what have you, is ammonia, and it steals a proton from water and makes this. So this is ammonia down here. This is the ammonium ion. It's to my knowledge, let's see, let me think about this. This one and mercury 1 are the only polyatomic cations. Think about that. We have lots of anions like NO3 minus nitrate. That's a polyatomic anion. Acetate, CH3COO minus. That's a polyatomic anion. But as far as the cations, most of our cations are metals, right? Sodium cation, calcium cation. All the different metals form cations. They're all singly atomic, one atom that's ionized. Mercury 1 is the Hg2 2+ cation. That's a polyatomic cation, and ammonium ion is the other polyatomic cation. So there aren't any others that we cover. Okay. Now this ammonium cation can donate a proton, so it can be an acid. So this could be a base, and this could be is called its conjugate acid. And so a species that's formed when a proton's removed from an acid is called the conjugate base of that acid, and the species that's formed when a proton's added to a base is the conjugate acid of that base. And again, I put these notes up on Blackboard so you have them. You don't have to draw everything. They're there for you in PDF format, and then you can rewatch the video. But look what's going on here. If I have water that's behaving like an acid and it donates a proton, it becomes OH minus, which is its conjugate base. And ammonia, if you put a proton on there, it becomes ammonium ion, which is its conjugate acid. So in this reaction, water plus ammonia, water is behaving like an acid, and it produces the hydroxide ion, which is its conjugate base. And then ammonia is acting like a base, and it produces its conjugate acid in ammonium cation. So any questions on this? This is a very important thing for filling out the reactions. A lot of times you're just given the reactants. And so how do you come up with the products? You take the proton off the acid, you put it on the base, and then you write the two structures. Okay.
So this will only happen if you have hydrogens.
Yeah, so if you just have a molecule that doesn't have any donatable protons, and most of the donatable protons are connected to some oxygen. Like this is water. The hydrogens are connected to an oxygen, and it's because the oxygen is pulling all the electrons towards itself. So it's really exposing this proton as a positive charge. And so then these electrons over here, can y'all be patient? It's still got 3 minutes. So this can come and steal that positive proton away. So
speaking of stealing protons, would that work with something like sodium chloride? Because sodium has that one proton living off. Or is it
no, you're thinking of the electrons. And so chloride has stolen the electron from the sodium. And so, yeah, so those are completely ionized, but they wouldn't have any effect. And that's a good thing to point out. Because the chloride is already so happy with its 8 electrons and its chloride minus, it doesn't want any more protons or anything like that. So it's not going to affect the pH. You can force it to make hydrochloric acid, but as soon as that gets into water, it gives that proton to water and stays its happy little chloride ion. And so that equilibrium lies so far to the right that we say it's a strong acid. It completely dissociates in water. And next time, that's when we'll get into strong acids and strong bases. And this is just the one I showed already, water reacting with an acid to make hydronium ion and a base. Okay, here's an organic base, which again, this nitrogen, it's an amine. It can steal a proton from water and protonate, make a positive cation, and then we have the hydroxide ion. And then here's water reacting with itself. So water can act as an acid or a base and produce hydronium and hydroxide ion. So thanks for sticking it out to the end. I'll see you next time.